Yes. A point in a strained material is subjected to stress as shown in figure. Using Mohr circle method without using any analytical approach. Determine direction and magnitude of major and minor principal stress, magnitude of greatest shear stress, the normal and tangential stress across the oblique plane AM. Draw the Mohr circle only in graph paper with suitable scale factor. Right? I saw a couple of numerical, and they're very particular that you have to draw the Mohr circle on a graph paper only. Right? So please ask for graph paper in the exam, and then you draw on the graph paper only. Okay, now let us start the solution. So let me just copy this. Given. Now from this, sigma x is 65 megapascal. There is sigma y also. Sigma y is 35 megapascal. And tau xy, see tau xy he has given in two places here. Now if you consider this, then it looks like clockwise shear force, and if you see this one, this looks like counterclockwise shear stress, right? So what you can do in such cases, you assume it as positive, or always take the direction with respect to the major or the normal stress in the x axis, right? So with respect to x axis, this is downwards, this is upwards. So this is making a clockwise rotation. So it will be positive, clockwise is positive. So 25 megapascal. Now theta in all our numerical we have taken with respect to uh, the vertical, right? Or with this uh, major normal stress. With respect to the major normal stress, the angle theta is taken. Now he has given with respect to the minor normal stress. So that is 45 degrees. Since the angle is 45, it will be same. If this were to be some other angle, then this angle would be 90 minus this angle, right? So here, since this is 45, both the angles will be 45 degree. So I'll just put it as 45, and 2 theta will be equal to 90 degree. Now I will start abacus also for drawing the scale diagram. I hope all of you are having the graph paper and the drawing instruments with you for drawing the Mohr circle diagram. Now, if you see here, this is 65 and 35. They are very small, right? So the maximum length in your Mohr circle will be 65 megapascal. So I will take a increased or enlarged scale, one or yeah, 1 is equal to 0.5 megapascal. I think this should be fine. So this will become 13 centimeter. 13 centimeter is sufficiently large, right? Now using this scale, we will be drawing the Mohr circle diagram. So let us go to the graph paper. Please draw along with me. Okay. So roughly I'll try to estimate what will be the diameter of the circle. Uh, Shear stress is 25 and angle is 90 degree. So it will not be, uh, this difference is 40. So 40 and 25 root of that, it should be around 50 or 60 millimeter, not more than that, right? So why I'm doing this, to estimate where to draw the more circle diagram, or to be on safer side, I will draw it at the middle of the drawing sheet. Now sigma x is 65, so 65 converted to scale will be 13 centimeters, right? So this is my reference line. Now I'll start from here, right? Let us start from this point. I'll call this point as O, right? Now from O, you have to measure 13 centimeters. So I just made this grids. So this is 5 centimeter plus 5 centimeter, 10, and 3 from here. So this is my 13 centimeter. So I'll just draw a small line there, right? So this, I'll call this point as J, right? Now this is representing my sigma x. Then you have to draw sigma y. Both are normal stress. Normal stress is on the x-axis, shear stress is in the y-axis. Now, what is the second one? Sigma y is 35 megapascal. So 35 divided by zero point 0.5 will be 70 millimeters. So from here you measure 70 millimeters. This is 50, 60, 70, right? So this is the point. So I'll call this point as A. Okay. So I have got this. Let me just draw a thin line here also to represent this point. Right. Now I got these 2 points. OJ is sigma x, OK is sigma y. Now what else is given? Tau xy is given, and that is positive 25 megapascal. Whenever you have positive shear stress, from here you have to measure it in upward direction. So I use a thicker line. So this is 20 and this is 25 right there. So this is my shear stress tau xy. I have to draw another line of same sort at K. So it's 20. Okay. This is 25. So it will be, I forgot to take it in the scale. It will be 50 millimeters, right? 25 megapascal divided by zero point 0.5. So it will be 50 millimeter. So from J, this is 50, and then from K, just like this. Please be careful because we are taking scales. So according to that scale, you have to take it out. Now let me call this point as D and this point as E. Okay, D and E. Now I have to join DE. So let's try to make this. Let me hide this. Yeah, this is quite big. I just join D and E like this. Now this point, this line is bisecting KJ at point C. So I'll call this point as C. Alright. Now with CD or CE as radius, I have to draw the circle. That is your Morse circle. So circle, I'll draw a different color. It's little tricky in here. Uh, are you guys with me? Is there any trouble anyone is facing? Please let me know. Yeah, approximately I just drew the circle. It became slightly elliptical, but that's okay because I'm not going to use this anyways. Okay, so with C as center and CD as radius or CE as radius, you draw a circle like this. Now from this circle with CE as your reference, you have to draw a line inclined at 2 theta. Now what is the angle of 2 theta here? 2 theta is 90 degree. So CE is my reference. So with respect to this, you have to draw a line at 90 degree. Let me just draw a line at 90 degree. Somewhere there. Okay. Now this angle is 2 theta. I'll just write that there. This is 90 degree. Okay. Let me call this point as, what is that we call? We call it as P. Right. Now after this, is everyone with me? Have you completed so far? Have you drawn this much?
Yes, sir.
Okay, good. Then what you have to do from here, it is very simple. You just have to drop a perpendicular. Let me use black color again. From P to this horizontal line, right? So this point will be Q. This is Q and this is perpendicular. So let me just show that. So that is perpendicular there. Now this circle is cutting the horizontal reference line at point, let this be H and this be G. Okay, so G and H. Now in this, what is the thing he has asked? Direction and magnitude of major and minor principal stress. So major principal stress is OG. From Morse circle we have major principal stress, so that is sigma P1 is equal to, what did I say, this is OG, right? This is the origin from here to this end, that is your major principal stress. So you have to convert this into scale. Then minor principal stress, sigma P2 is OH, right? OG, OH. That is your principal stresses. And what else is asked? Direction and magnitude. You have to find both, right? So the magnitude will be this angle. So let me just show this. Or I can just write CJD. Inclination of major principal plane this is theta P1. Actually it is 2 theta P1, not just theta, because I have drawn this Mohr circle with 2 theta, angle 2 theta. So what you get for the principal plane is also 2 theta P1, right? So 2 theta P1 is JCD, angle JCD. Do we have symbol for this? Forget it, I will just write it as angle JCD. So you have to measure that angle. From that you will get theta P1. So JCD by 2 will be theta P1 and theta P1 plus 90 degree will be theta P2. Okay, that we will do it later. Then he has asked magnitude of greatest shear stress. So that is tau max. Maximum shear stress tau max. So tau max is the radius of this circle. Now what is the radius of this circle? It is CD, right? Or I'll just make another point here as Y. So CY is the radius of the circle and that is the maximum shear stress, CY, tau max. What else is asked? The normal and tangential stress across the oblique plane AM, right? So normal and just copy this. So normal stress is sigma n. Now what is sigma n? In this diagram, the sigma n is OQ, right? So this is the same thing what we have done earlier. So this is OQ and tangential. Tangential stress across the plane AM. This is tau. Tau is equal to PQ, right? This height, PQ. Now, why did I say YC is the maximum shear stress? See, shear stress is along the y-axis, normal stress is along the x-axis. Now, if you go on moving this point, shifting this point and bring it along such that CP is on the x-axis, then the shear stress will be 0. Now, if you move on this point towards right, and if P comes to Y, that is the maximum value of shear stress you can have, right? So that is why I said the radius of the circle is the shear stress. Now what you have to do, you measure these quantities from your Mohr circle, convert it back into the scale that will give you the stresses. Prasad, please mute your mobile, right? Now for this, I will just recreate this in this software. Okay, let me quickly do it. Please calculate these things. I'll just put it on the chat so that you can find it. Please find these values. Okay. Meanwhile, I'll just quickly do this on Abacus so that we can check the answers. So first, I have to draw a line of 65 megapascal. So from here, I'm using 1:1 scale so that it is faster for me. And then another line from here, which is 35 megapascal. Maybe just dimension this. This is 35 and this is 65. Right? Now the shear stress is 25 megapascal. So I'll just draw another line like this. Okay, so I'm just dimensioning that. This is 25. This is also 25. Right? So they are intersecting at this point. Now I have to draw the circle with this as center and this will be the radius. So I got the merchant circle now. Now I have to draw the inclined plane. Where is my diagram? Yeah. So from here at 90 degree. So I'll just draw a line like this. And this angle is 90 degree. Now you drop a perpendicular from this point. So this is the perpendicular. Now I have everything. I can just find the values. So first principal stress is sigma P1 is OG. Now OG is from here to here, right? That is the maximum shear stress. So let me find this from this point. Okay, I cannot do that. I'll just draw another line from here. I should be able to do it. So from this point to this point, this is 79.15. So this is equal to 79.15. Since I have used 1:1 scale here, so I am getting directly this answer. So you should be getting 158.3 mm. And that will be 79.15 megapascal. Now you have to multiply this length by the scale, which is 0.5, right? So OH, this is OH. Again, there is no point, I cannot measure that. So I'll just draw a line like this. And let me measure from here to this distance. So that is 20.85. 20.85 megapascal, right? 20.85 into 2, 41.7 mm. Okay, angle CJD. CJD is this angle. So let us measure this from here to here. This angle is 59.04. 59.04 degree, or this is 2 theta p, theta p1 is equal to 59.04 by 2. Now please don't convert the angle to scale, because angle is not scaled anytime, right? Angle remains as it is. Some students scale the angle also. So since this is 2 theta p, I am finding theta p by dividing it by 2. 59.04 by 2, 29.52. 29.52. Okay, so this is the major principal plane. Similarly, minor principal plane to theta, sorry, directly I can write theta T2 is equal to theta P1 plus 90 degree, right? We have done this earlier, that the two principal planes are mutually perpendicular. So I'm just using that. So this will be 29.52 plus 90, which is equal to 119.52 degree. So I got both the principal plane directions. Then maximum shear stress is Cy, which is equal to, let me measure this. Now I don't have Cy there. Let me just draw a line like this and then dimension that. So this is 29.15. 29.15 and the A 29.15 is 58.3, right? Now the normal stresses for Q. So this is Q from here to here. I have to measure the dimension. So from here to here. This is 25.0. 25 megapascal, or it should be 50 mm. And last, there was tangential also, right? Megapascal. That is PQ. Let us measure this. That is 15. It will be 30 mm equal to 15 megapascal. Right? So you found all the things that is asked in the question. Direction and magnitude of major and minor principal stress. So that is this up to here. This is magnitude, this is direction. Then magnitude of greatest shear stress. So greatest shear stress is tau max. We found that. The normal and tangential stress across the oblique plane AM. So we have found normal and tangential stress. In case if they ask resultant stress, then it will be line joining these two. Let me just do that also. Just join O and P like this. Now measure this length. So this is 29.15. Resultant stress sigma r is equal to OP, and that is, how much was that? 29.15 megapascal, 58.3 mm, right? So this is the solution for this.